Hello again. In the last lesson, we looked at different properties of waves like wavelength, frequency, amplitude. Those were all characteristics of waves that you probably learned about in grade 10. Most of what was in the last lesson was probably just review. Today we're going to look at something that should be new, and that's the idea of interference of waves. So interference is when two different aspects, two different objects, or two different phenomena come together and cause a different effect. They have an effect on one another. That's what interference is. And so when we look at wave interference, we're looking at how one wave will affect other waves. So let's say we have two waves, and they're going to meet. Remember that each wave is a result of the wave that you see is a result of the displacement of individual particles from their equilibrium point. So when you have two waves that meet, it makes sense that both of those displacements would be added together. So when this happens, there's only one medium in which the wave is traveling, so you can only see one wave. But the wave that you're seeing at any given time will be a result of both waves adding together. We call this, got a really complicated sounding name for a relatively simple thing. We call it the superposition principle. Superposition means to kind of lay one thing on top of another. The easiest way to demonstrate this is actually to look at not a wave but a pulse. The difference between a wave and a pulse is a wave is a continuous motion, whereas a pulse is just one part of a wave. So let's say a pulse. I'm going to draw this in blue coming from the left side here. So let's say this black line represents a string. And so when I send a pulse, I can take my hand and kind of whip this string up, and I'm going to send a little pulse towards the right. And that will be my pulse. It's not a full wave. If I were to keep doing this over and over again, then it would be a wave. Let's say I do the same thing going back in the other direction. That was supposed to be the same size, but it's not. That'll be good enough. So they're going to eventually end up meeting. And I can take my waves over here, I hope, and slide this one along. And then this one's going to come along. And eventually you see that they are going to meet. Let me adjust this guy a little bit so that they are approximately the same size. Close enough. So now the question is, what's going to happen when they come together? Well, when they first come together, you'll see that they're only partially overlapping. So the points that are overlapping, each one of their individual displacements will add up. So let's look at this right here. So at this point right there, there's no displacement from the green wave. A blue wave has its own displacement as well. Same thing happens over here on the other side, where the blue wave has no displacement, but the green wave does. In the middle, their displacements end up adding together. So when you have both of these, you've got a little displacement from there to there, but you're going to double that. So one for the green wave, one for the blue wave, it would add up together and you'd get a displacement somewhere in that range. And so our wave from this point to that point might look kind of like this. So at this point in time when the waves are together, the blue wave will look the same way that it looks. The green wave will look the same way that it looks. But when the part where they overlap would look kind of like the red wave. So what you would actually see is this. And at this point in time, you're probably thinking, boy, this is really difficult to draw. How am I supposed to draw these waves coming together? I would say don't, or at the very least, don't do it until the very, very end. Let's look at, on the line below, let's look what happens when the waves are together. So you've got that wave and then completely overlapping it. Arbitrarily, I kind of picked waves that were the same amplitude and the same wavelength, so you'd have them totally overlapping. So what you'll get when they go together is you add up each one of the displacements, which is essentially going to double the total displacement. So you get this kind of really large amplitude. You get a much larger wave. So we call this, the idea here is that we call it constructive interference. Constructive meaning that you're making more out of it than you originally had. It's sometimes easier to demonstrate this with waves that are not exactly the same. And so let's say that I have, I'll use blue and green again. Let's say I have a square-shaped, a rectangular-shaped wave moving towards the right. And then I have, on the other side, a triangular-shaped wave. We'll say that they have the same approximate wavelength. The wavelength being the point from the beginning of the wave to the end of the wave, even though it's just a pulse and not an actual wave. So it's coming back the other way. So what's it going to look like when they meet in the middle? So easiest way to do this, what I'd like to do is use a little dotted line. So there's my rectangular pulse. Here is my triangular pulse. We assume that they're going to have the same wavelength. Now we need to look at adding those together. So at the very beginning, you don't need to add every single point. You don't need to manually add every single point at every one of those little dots. You just look for kind of trends. And so at the beginning, the displacement, there's no displacement from the green, and all the displacement comes from the blue. Now the blue displacement is going to stay the same while the green goes up to this peak. So let's look at right at the very middle here, right at this point, adding the two displacements basically doubles it, and it goes up to here. And on this end, you get the exact opposite. You can try to look for some symmetry as well. So what you get is the wave would look, there's no displacement over here. It would just jump up to that point, go up diagonally over to there, down diagonally over to here, and you get this little house-like looking thing. What is the actual use for this? You've probably never seen a square wave, on a water wave coming towards you, and it's totally square or totally triangular. Yeah, this doesn't happen much in nature. You can use computers to generate waves, and there are reasons for them. Anyone who deals with oscilloscopes or any kind of sound generation, if you're thinking of going into music production or whatnot, or going into computers, you may see something like this. For right now, our purpose is just to show the processes that happen with interference. So this is constructive interference. The waves interfere constructively, adding to their displacements. Let's just below that, let me add a couple of lines here. So let's look at same type of thing. Here's a regular pulse, and on the other side I'm going to draw another regular pulse, but I'm going to draw it on the other side. I'm going to draw it inverted. And so when they come together, you're going to have the blue pulse on the top, the green pulse on the bottom, and as you can imagine, at this moment, when they're completely overlapping each other, you would end up with total cancellation. So they are destroying each other. So we call this destructive interference. In the middle points, if you're trying to think of what this would look like in the middle, we can back that up and we can back this up a little bit. Obviously, the first part would look like it would normally just be the blue wave, and then you get down to right about there and things are going to be different. In this part here, it's going to look like the green wave, and you get to right about here and things are going to be different. Really, you're just kind of joining the two. When they add together, they're going to make a pulse that looks kind of like that. Or like so this, at this point, would be, it'd still be destructive because we're not in this zone on that side and in this zone on that side. There's no interference that happens whatsoever, but in the middle, they act to destructively interfere with each other. So what does this look like with our rectangular and triangular pulses? There's our rectangular pulse on one side, our triangular pulse on the other side. So take a second and try to draw what this is going to look like. This would be a good time to pause the video for just a second. Okay, if you're back, you're ready to see what this looks like. So I'm going to add my two pulses together. So at the beginning, I have everything from the blue pulse and everything from but there's nothing from the green pulse. Same thing over here. At this point, if those heights are the same in the middle, right in the middle, if the heights are the same, then there's no displacement there whatsoever. So what you would see here is nothing to start with. It goes way up to here, same thing on the other side, and in both cases they work their way down towards the middle, so you get an M-looking type of shape. So this is destructive interference. So the principle of superposition, you just add the individual waves. This can be found in your textbook in section 6.6. So you notice that we have that we skipped 6.4. Well, we'll come back to 6.4 in a second. We've skipped over 6.4 for a second, and 6.5 we're skipping over completely. All right, speaking of 6.4, we want to look at the way that waves will reflect. In your textbook, they talk about reflection off of fixed end free ends. We're just going to look at fixed ends, so that's all that's really important to us right now. So imagine this diagram here. The black line, the dotted line to be like a string or a slinky that's stretched very, very tight and fixed to a wall. So here is our fixed end. So that slinky is, or string is firmly attached to the wall. You've probably seen in grade 10 the waves that you can generate using a slinky. I will demonstrate this on Thursday as well. But for right now, we're just going to have to use our imaginations. So let's say, and this is probably going to be a little bit complicated, so let's hold off on drawing these things until maybe we're done. So let's say we have a nice pulse coming in here to the right. So that pulse is going to move where the dotted line is underneath of it. That's part of the string. That wouldn't be there anymore. That would be following the blue line. And so really you could just draw this blue line extending all the way until the fixed end. So that pulse is going to move along, move along, move along, move along, move along. And eventually it's going to hit this fixed end, and that's when the interesting stuff starts to happen. Okay, so let's move down to the next line over here. So this first point is where the pulse starts to hit the end. Now let's imagine that the pulse hits the fixed end and wants to go straight through, because that's really what it wants to keep going. Newton's first law wants to keep traveling in the same kind of direction. So let's just draw that. In fact, clone. Oops. There we go. And let's say that it wants to keep going. So that's what it would normally look like. But obviously it can't go through the wall. Here's the other problem that you have. I said that right over here, that is a fixed end. Fixed means not moving. So this point directly above it, right here, can't move. It can't be up there. So what basically is going to happen, if we back this up just a little bit, back that up, erase that. Okay, so this point on the wave now wants to move upwards. Based on what's coming behind it, that's how the wave moves, if you remember from the last lesson. It wants to move upward, but it can't because it's fixed. So it means that the wall is applying a downward force on it to prevent it from moving up. And in doing so, it's going to not just pull it down. The whole reason that the slinky or rope can achieve this wave, this pulse, is because there's a little bit of stretch in it, some elasticity to it. So the wave wants to go up. The string at this point wants to go up, and so it stretches. Because there's a fixed point that won't allow it to move, but it wants to go up, so it stretches. And then just like it would with an elastic, when it reaches a point where it can't stretch anymore, it rebounds and heads and compensates by going down. So what's going to happen with this point is it's going to be pulled down below the axis. And so what we get is, after a little while, when this wave would have moved through a little bit, obviously this part here can't do that. But how it ends up showing up is on the other end, it shows up as a kind of downward wave. And so we would see that it actually will reflect when we keep going here, when this thing continues to move, the wave basically keeps going on the other end and moves back. So you end up with the wave looking like this, not drawn to scale apparently. You end up getting this heading back the other way. And so what we call this is, there's a whole bunch of different names that we call this phenomena. The blue wave comes in, it reflects, it goes back out as a green wave that's upside down. They don't actually have different colors. I just drawn them as different colors so you can identify them. So they come back inverted or flipped. We call it a phase change. We call it a phase shift. We call it an inversion. There's a whole bunch of different names for it. Doesn't really matter what we call it as long as you recognize that it would reflect upside down. Just so you know, not that we're going to need it, but if this was a free end, then the wave would reflect on the same side, in phase instead of out of phase. I can show you what this looks like. Move on to the applets here. Actually, okay, so I have a fixed end, and I have a source. You probably recognize this applet from last time. I'm going to actually generate a pulse. And I'm going to take the damping down so that it doesn't lose any energy. I'm going to leave the amplitude where it is, and I'm going to generate a pulse here. There we go. Okay, so you can see the pulse is moving down. Let's fiddle with the tension a little bit here so it can go a bit slower. And reset and try again. Okay, not that much slower. Reset, try again. Okay, so here we go. And we can see, boom, when it comes back, it goes back down the other way. So another pulse is generated, and boom, it comes back down the other way. So you can see that happening. What we want to look at now is a very special case of interference, because you'll probably notice if we go back on the last diagram, if we look at the second one here, we've got the blue wave coming in, we've got the green wave coming out. Well, that's really the interference. They're going to interfere with each other the same way that they did over here. You've got one on the top, you've got one on the bottom. They're going to interfere together, just like in this diagram right there. So, this is just with one pulse. But what happens when it's not just one pulse? When the wave keeps coming and you get the blue pulse coming in, or a blue wave coming in like this, and then you're going to get a green wave. Now that green wave, remember we said, is inverted. It comes back flipped over. So it's going to come back a little bit like this. And you might think, well, we're going to get destructive interference. And sometimes we do, but at other times we don't. So when the reflected wave interferes with the incoming wave, let's see what we end up getting here. So instead of a pulse, I'm going to have an oscillation, and we're going to have to fiddle with this. So hold on a second. We're going to have to fiddle with this just a little bit, and let's see. Heighten our tension. Let's bring our frequency way down. 17. Reset. Not that far down. And if we organize it just right, we can see that we get this really weird type of wave happening here. Okay? This is what we call a standing wave. And I'll show you how it works in just a second. Looks a little bit chaotic there, but so the resulting wave that we get is called a standing wave. And if we go back to the applet here for just a second, well, for a couple of minutes actually, we'll go step by step and we'll see how this is. We'll see how this is working. Reset this. Pause. And we'll go forward step by step. Now there was another applet that I had that was way, way better for showing this. It would show both the incoming and outgoing waves. This one doesn't do that, so I'm going to try to improvise the best I can. Okay, so we have this wave coming in. And so when it reflects, and we'll see, we'll draw this the incoming wave here in red, the outgoing wave, it's going to, well, let's draw it this way. That green wave is what it would look like if it were to keep going. But it doesn't want to keep going. It reflects. So you would expect it to do, but not only does it reflect, but it also inverts itself. It flips. So it would look like that. So let's draw this coming back. And so it would look something like this. And at this point, we don't get either constructive or destructive interference. They don't match up. But if we keep going step by step here, let me erase this. If we keep going step by step, let's see what we get. So you notice at this point that, take a look at the amplitude here. The wave, the amplitude of that wave is way higher than what the incoming wave is. The amplitude is very closely related to the amount of energy that's in the wave. So it kind of looks like we're getting more energy out of nothing. But what's happening is that the energy is building up. Every wave is carrying a little bit of energy, but we have two waves happening here at once. So what we actually have, if you notice that the wave that is coming in, again, I'll draw it in red, would kind of look like that. So the green wave, that would keep going if you were, if you allow this wave to keep going, it would do something like this. But it's going to reflect. So there's the reflect, and it's going to flip, because when it hits a fixed end, it reflects flip. So it reflects like this. So now those two waves are totally overlapping each other, and the result is the blue wave that you get here at that moment in time. If we allow this to run a little bit more, you can see that we go through periods of constructive interference like we have here, and then a little bit later, looks like the wave totally disappears. What we're getting is, again, let's follow the red wave here. It would reach its minimum over here, and a maximum up there, and a minimum over here, and a maximum up there. Let's try this over again here. Notice that where the green dots are, there's your trough, crest, trough, crest, trough, crest. Okay, so now imagine this wave were to keep going. So it keeps going, but it can't keep going because it hits a fixed end, so it reflects. And so it reflects like this. But remember when it reflects, that it has to invert itself. It has to flip. So that point, if it's flipped, actually comes down here. So the wave that is reflected would look like this. Excuse me. So you can see total destructive interference every step of the way. So the red and green wave interfere with each other destructively, and you get this. Well, nothing. You get nothing. The wave totally disappears. That's the destructive part of the standing wave. So you notice at a certain point of time, in a couple of seconds ago, we had constructive interference where we had these huge amplitudes. Now we have basically no amplitude. The waves totally destroy each other, so you get destructive interference. So a standing wave will actually end up being alternating between constructive and destructive interference. So constructive, destructive. And so if we have everything at just the right frequency, here, there's our constructive part, there's our destructive part. Constructive. Now the frequency isn't quite right to make this work perfectly. Which brings us to the next point, that the frequency just has to be just right. So we notice that the waves alternate between constructive and destructive interference. Both the troughs and the crests are twice as high as the original wave. When we have everything working properly, when I could set up just the right frequency. For this length of whatever it is, rope, slinky, string, whatever, for that particular length, there are only certain frequencies that will allow that to happen. Let's look at how that works. So notice that we have a very particular shape for our standing wave. It basically looks like it's an individual wave at times. And there are points, if we, let me see if I can just edit this, just fiddle around with this frequency just a little bit and see if we can get a better standing wave here. Slow it right down. No, that's not it. I'm definitely going the wrong way. Let's try that. Not too bad. What I'm looking for is the green dots. If we time this perfectly, the green dots will stay in exactly the same spot. They won't vibrate, and you can see on the right side that they're kind of like that. It's not perfect. They are vibrating a little bit, but they're pretty close to staying still. And so I think that's probably about as good as we're going to do. They vibrate a lot more on the left side, but on the right side you can see that the green dots are pretty much stationary, and that's an important point. Let's pause this. Go back to here. So let's consider a string of length L. So notice in that case that we had the wave kind of alternated between kind of looking like that and looking like this. That is a poorly drawn standing wave, but it's close enough. Let's try that again, actually. Might help if I put a little line here. And just to make things a little bit easier, I'm going to insert a ruler. And let's put little dots there, 4, 8, 12, and 16. Get rid of my ruler. And so the standing wave kind of looked a little bit like this. So at one point, it would have looked like that. And then it would have gone into destructive interference, where it'd be completely flat. And then it goes back to constructive interference, where it looks a little bit like this. So that's what a standing wave tends to look like. What you'll notice is that there are a certain number of waves that happen to fit into this length. So in this case, notice that we have one wave, goes like that, and then we have another wave. Those are two waves. So this whole thing takes up two wavelengths. So 2 wavelengths equals the length of the string. So the wavelength is half the length of the string. So that tells us what the wavelength is. Now the speed of the wave in the string is set. It is a function mostly of the tension in the string, but it's also of the density of the string and a bunch of other stuff that we'll get into in chapter 8. So we'll just say that the speed is v, which means that the frequency that we need to get this particular wave frequency is the speed divided by the wavelength, or the speed of the wave divided by L over 2, which means 2 times the speed divided by L. That's for this particular wave. The simplest standing wave that we can get has basically just one fixed end on the very, very end and one other fixed end on the other end. So it would look like, kind of like a skipping rope. It would look like that. That is the simplest fixed or standing wave that we can get. So again, the length of the string is still L. Now, how many wavelengths are in that particular length? Notice that it's not a full wavelength. You would have to keep going. So that's only half a wavelength in between this point and this point. So here is half a wavelength. These 2 points, by the way, those fixed ends and these points in here in the middle that never, ever, ever move, those green points that we were talking about on the applet, those are called nodes. The the crests and troughs are now actually called super crests and super troughs, and they're not nodes, they are antinodes. So in this case, we have two nodes, 1, 2, and we have one antinode right in the middle. If we look at the speed of the wave is not going to change. The speed is just equal to v. The wavelength now, half of a wavelength is equal to L. So lambda is equal to 2L. So the frequency, using the wave equation, is v over lambda, which is v over 2L. So that is the simplest standing wave. The next simplest standing wave would contain one node in the middle. So the length stays the same. Notice that we have one wavelength in here. There's half a wave, there's the other half of the wave, so that is one wavelength. So lambda is equal to exactly L, so using that we get F is equal to V over L. And notice that this is exactly twice of what that is. So we call this, if we call this F naught, then that would be, the second standing wave would be 2F naught. And we'll get back into this idea a little bit later. But the main thing that I want to point out to you is that this frequency to create this wave is twice the frequency to create that wave. Notice that if we go back up, this frequency over here is 4 times the frequency to create that simplest wave. So only frequencies that are multiples of that simplest frequency, there's only certain frequencies that will allow us to produce a standing wave. And if we go back to look at our applet, and we produce a standing wave here, let's see if we kind of produce a standing wave. It's close. If I change this frequency to, say, 61, there we go. And so I'm not really getting the standing wave anymore. We get a whole bunch of really weird stuff. It kind of seems to go crazy for a little while, and then it calms down at some points, so this is not a standing wave anymore. We're not at the right frequency. Only particular frequencies can give a standing wave, because you have to fit a certain number of wavelengths into a limited space, into that distance L. So we're going to look at the effect that this has on actual everyday objects in the next lesson. So as far as your hit list is concerned, we have now looked at 6.4. You can kind of brush through that fairly quickly. There's not too much there. We skipped 6.5. We did interference of waves in 6.6. I would try a few of those on your page. I'll get to 6.7 later, and we've done the standing waves part is 6.8. So I'll come back to 6.7 in the next lesson, and that will be it for chapter 6.